It's me and Ben.
Hi, good morning.
Troubling. Where's the rest of our team?
Yeah,
Hmm. How you been?
pretty good. Yeah, I had a pretty nice winter break. How about you?
Yeah. Yeah. Enjoyable.
Good.
Very enjoyable. Always goes fast, but
Yeah.
that was long.
And
Shouldn't have went that fast. Landon's here. Let's see. Let's give everybody a second. Evel's is here. I will show you guys something I've worked on recently. Let's see. Right. There we go. That's that guy. So what do you guys think you're getting yourselves into here? What is statics about?
Oh, I know I had a chapter on statics and physics, so
Oh,
I
interesting.
feel like got some kind of taste into what it is. But
Yeah, a little bit of an intro. Well, I'll show you guys something that I did recently. This was where did that go? This was a plan that I drew back in 2019, so it isn't super old. So here's kind of the property from the air, and here's what the house actually looks like. Let's see, that's the garage. Where's the house? It's over here. So I've never done one of these before at the time, and basically this is kind of a modern looking design. And welcome, Aaliyah. And I've just given a quick intro to kind of what statics is really all about. And so you got this awning roof that sticks out. It's kind of a cool, you've seen that perhaps in different places before, I don't know, but that awning is not going to be able to hold itself up there. So, oh, I know, let's put a cable holding it back over here. And basically what we want is for this thing to remain, well, static. Static is kind of code for not moving. Next term, we'll look at dynamics, which is where things do move, because sometimes you do. I mean, if you have a backhoe that's digging dirt and so forth, there's all kinds of motion there, and I want it to move, and I want to understand how it's going to move. And so dynamics is sort of the branch of mechanics where things move, and statics is the branch of mechanics where things don't move. And this is a huge, I mean, assuming you're all going into engineering, this is a huge backbone of what you do as an engineer, is try to keep stuff from moving. And in this case, it's kind of like, well, okay, great. If this thing has weight and you screw it to the wall, it obviously wants to kind of pivot down, and so it's going to put tension, pulling force on that cable right there. And so the question is, okay, well, how big does the cable need to be? And how do I attach it to this in such a way that the bolt doesn't shear off? And how do I attach it to the wall in such a way that it doesn't kind of pull the wall over? And in a sense, and I had to submit that to an engineer, even though I teach engineering, I don't have the stamp for it. In a sense, that's what you're going through college to do, is be pass the engineering test, PE, the professional engineering test, so that you can stamp things as well. And it's going to be based, your stamp is going to be based on the calculations that you make for this. And the calculations he made for this that he sent me that I had to turn in kind of to the city and so forth are the same calculations I'm going to teach you how to make today. So this is a very much you're learning something here that will make you money that not very many people can do. So it's kind of cool. So let's see. I already know all of you except for Aaliyah. I don't know you, Aaliyah. Where's your background? Where did you come from? Hit the space bar if you've never used Zoom before. That takes you off mute. Or in the lower, I can't hear you, Aaliyah. Over in the lower left-hand corner, there's a mute that you can click with your mouse, but there you go. What's your background? How'd you get here?
I've lived in Cave Junction my whole life, and I don't know, I want to go into renewable energy engineering, and
Okay.
I've been going to RCC for 2 years.
Sweet. Okay. Outstanding. I know the rest of these folks from calculus, usually because calculus is a prereq for this class, and I taught calculus last year. I had all these other folks in calculus last year, so I know all of them. I know them. But having said that, this is not an easy class. This is going to push you. And it does have physics as a prereq, and it does have calculus as a prereq, and we won't need that all the time, but there'll be times when you need to know that. Now I'm going to try to teach it as though you've never seen that before, but we're going to rely on integrals and derivatives a little bit in this class, which is sort of cool in a sense to think that all that went for something. But also it's going to grow your understanding, because it's one thing to kind of pass a calculus class. It's another thing to know it well enough to apply it to something. And so between statics and dynamics, we'll play around with that a little bit. And so you'll see that applied in a way that's just fantastic. And so it's really cool. But it is a challenge. One of the things I'm going to do in this class is I'm only assigning, and you have the syllabus now, I think, I'm assigning kind of fewish problems, because they're challenging and they're, very representative of kind of what you need to know. But most importantly, I would say the answers to those questions are in the back of the book. Like, with maybe one or two exceptions, I only assign questions that have the answers in the back, because these are hard enough that you need that. You can't wait for a week later to find out when I grade it that you didn't do it right. Like, you need to know it's wrong and do something about it immediately. And as did I print my syllabus? Kind of forgot about that till just now, but as I noted on my syllabus, I have office hours kind of after this class, and my intention is to be sitting in the Zoom link that I put there for every day, so that you can kind of check in. At least you can find me then. But you're also welcome to email me and have a quick Zoom. It's like 7 o'clock at night. My kids are all raised, and if I'm home and you have a question because you're working on it after work or something like that, you don't have to wait till that time. I mean, I'll hit you up and we can talk one-on-one about it. But you're going to need that, as my point. And to make connections with people in this class so that you can work together on stuff is an excellent idea. So I'd encourage you to kind of get to know each other a little bit in that regard. Bouncing ideas off each other is really important. But I will say that and people that I taught calculus to already know this, my penchant is toward making you, or helping you understand, reason this out, not follow a memorized process by which you can get the answer right, but actually to learn to think. Because you're going to end up assigned as an engineer things that you haven't seen before. And if you don't learn how to think, you're not going to be able to get it figured out. And secondly, it's going to be a long time before you actually are asked to do this, and you're going to forget it if all it is blind memorization. Blind memorization is ultimately kind of worthless. So I'm going to spend a good chunk of my time teaching you guys, helping you reason out how things like this work, how statics works, how you keep things like that roof I just showed you, well, static, not moving. The essence of all of statics is, if something is moving, then it's falling. So you've got to keep it from moving. Given that Daniel and Aaliyah added late, I doubt you guys have the book yet. But chapter 1 is real important to read. I sent you guys an email about that a while back. And one of the things it talks about is Newton's laws, and his laws of motion. And we're going to use those today. And the main thing is this, like, I'm sitting in a chair right now, and I'm static, like I'm not falling through the floor, but I have weight, right? I have a force. I have 180 pounds pushing down on that chair right now, and I want to go down. Like, the gravity is the main sort of cause of failures of bridges and all those kinds of things. You also have wind and seismic and so forth, other things you got to calculate for later on. But the main one is just in terms of your beginning in this process is just gravity. And so one of Newton's laws, I think it's the first one, says for every action, there's an equal and opposite reaction. The fact that I'm sitting here static, even though 180 pounds is calling me to the center of the earth, is the fact that the chair is strong enough to push back up. You can appreciate if you sat on you've probably all fallen through a chair at some point maybe, but if you sit on something that isn't capable of withstanding that force, then you're now dynamic, you're moving. So your job is to basically say, hey, that roof weighs a lot and it wants to fall to the center of the earth. Well, what are you going to do to stop that? Well, let's attach a cable. And what angle you attach it at is really important. And I don't know if that kind of feels like it makes sense to you, but let's start playing around with that kind of right now. So what am I doing? So for the most part, what we're going to do every day is I'm going to pick problems from the book, and I'll show you this one right off the bat. I'm going to pick problems from the book that I think are kind of representative of what you're going to do in your assignment and use those as kind of our discussion topic for each day. And then in my open math, I'm going to post these notes after class every day. And I'm also going to post this live lecture every day. It's a little hard to go. I mean, if you miss a day, that's what the lecture is going to be good for. But, you know, even if it was like, yeah, I talked about something in there, let's go watch that again. So you'll have access to all the stuff I do. The thing I don't want you to do is to spend all your time writing notes on this stuff. Realize that whatever I'm writing on, and mostly that's what I'm going to be doing, is pulling these up and writing on them. You're going to have that. So the more you can be present and immediately interrupt and ask questions and, you know, think. I'm going to try to give you think time, but interrupt and say, that doesn't make sense to me. And then, you know, give me the opportunity to say a few more things about it. Let's save that for a second and let me, so we're really going to spend kind of 2 days on chapter 2. And really today we're going to tackle 2.3 and 2.4. And you'll notice in this book that not every section has an assignment. So in this book, 2.1 and 2.2 are kind of introductory, and they're really short. And if you've never been in the habit of reading the book, you want to start, because this stuff is not something you can just watch me do and get. If you want to really get this, you should be reading ahead, like ideally today, because we're going to cover the first part of chapter 2. If you had read 2.1, 2.2, 2.3, and 2.4, and maybe even looked at the questions that I was going to assign that you have to do, so that when I talk, you already have some questions that I'm answering. That's going to be essential. If you don't ask your own questions, then the answers that I give are not going to be near as meaningful to you. But one of the things chapter 1 talks about is how you can reduce things to a particle. In other words, if I say, all right, I won't even draw it out, but let's just say that's a book. I mean, if a book weighs, or even me, I was talking about me a second ago, I weigh 180 pounds. The book will describe that as a particle. In other words, you don't have to think of it as having mass and size and shape and all this stuff. You can just think that's a dot weighing 180 pounds and it's in a location. And so, for instance, if you wanted to draw a picture of what I just described, it would be, here I am, here's the particle of me, and there's a force down, thanks to gravity, of 180 pounds. And you may know from physics, there's a difference between weight and mass, and that'll be important in this class. So if that's what you see in this diagram is a particle, a dot with 180 pounds down on it, then it's going down. There's no other forces. Now, if you as an engineer say, I'd like to stop that, then you're going to have to push back against that. Does that make sense? That's the concept of equilibrium, and how in order to get it to stay static, I got to pull against it. Now, the easiest thing I could do would be to pull straight back up at 180. In other words, if I attached a cable to my back that was strong enough to pull up at 180 pounds, then that would keep me still, right? Or I could take that 180 pounds pushing down, and I could put a chair underneath there that was strong enough to push back at 180 pounds, and now it would stay static. And so that's what you need to have. You need to have equal and opposite forces in order to make things stay static. You could even do this as an option, which is about the problem I'm about to introduce. Let's say you hung 500 pounds right here, but what if you weren't able to push directly below it or directly above it in the same exact line that the force is actually going. Could you pull in this direction and keep that from falling? Somebody say something about that.
If you had a third vector that you could add to cancel the other two out, so they all at 0.
Yeah, so you're bothered. Daniel's making a point that you need a third vector. He's actually right about that, but I don't know if you agree with him yet. Would this work? Would this keep me from falling if you put 500 pounds of force right there? And think of it as just a rope. It's a tug of war. You have 2 ropes attached and you pull it 500 pounds. Is this point still going down? Or is it now not moving vertically?
If it's the same amount of force, then it'd be moving down and to the right.
Yeah, based on trig, do you understand that that vertical component of that 500 right there is going to be less than 500? In other words, 500 kind of represents the hypotenuse of this. And so for instance, if I said, I'm just guessing based on what I see here, but if that was 40 degrees and your hypotenuse is 500, then you'd actually have to do trig. And so I'm going to get my calculator out, get out of radian mode where I am when I teach calculus. You're going to be in degree mode all the time in this class. And I say, let's see, that vertical component over there, let's see, if I said the cosine of 40 degrees, that would be adjacent over hypotenuse. And so if I take 500 times the cosine of 40 degrees, I get 383. And so the vertical component of that 500 is only 383. And so do you see how that angle that you attach that force at, or the angle you're pulling at, isn't going to work? Like this is still going down. Does that make sense? Now, in order to keep it from going down, then you'd actually need this number to be not 383, but 500. But does it make sense if you needed this number to be 500 up here so that it stayed static vertically? Then that means the actual size over here is going to have to get larger. So now I would say, okay, well, if this is going to be 500 and this hypotenuse over here that I don't know, I'll say question mark, is it 40 degrees? Then I could say, well, I guess the cosine of 40 is adjacent over hypotenuse. I could solve that equation. And so in that case, I'm going to take 500 and divide by the cosine of 40. 500 divided by the cosine of 40. And that's wrong. I put cosine of 4. That's 6. I'm just going to round it off. 653. I'll even say approximately 653 pounds. And so could you actually come back if you had 500 pounds that were going to go down here because you had a roof that you were going to support and it weighed 500 pounds? And you said, could I have a cable that went off in this direction at 40 degrees that would actually make that static? And the answer is yeah, as long as that cable, or just again, think of it as a person pulling a rope, as long as that person pulled at 653 pounds, I'll get pounds in here, then that would actually balance that load vertically. Do you agree with that? Do you see the logic there? So it makes a difference what angle you attach things at. As I said, it's the simplest to attach it vertically because then you would just need a 500-pound cable or a 500-pound pull, and that would create it static. But do you also agree with what Daniel said earlier? Does it make sense that that particle, which again represents the center of mass of that maybe big heavy roof or something, does it make sense that's not static? Why isn't it static?
Still receiving a net force to the right because there's still a horizontal component to that pulling force.
So the very fact that you attach that cable kind of at an angle means it's also pulling to the right now. And so now this thing might be sort of stable vertically, but now the particle actually has a force on it horizontally. And couldn't we use trig to figure out what that was if we wanted to? If I came back and called this H for horizontal, I could say the tangent, and I'm reviewing your trig skills for you right now, because that's going to be, we're going to use trig so much in this class, it's going to be insane. And fortunately, it's all kind of basic trig, like SOHCAHTOA trig. So tangent of 40 would be h over 500. And so that would mean h, if I take 500 times the tangent of 40, that gives me 419.5. So I'll call it approximately 420 pounds. So basically that has a net force of 420 pounds that wants to go to the right. So I'll add that to this picture just so that you see that. So it's actually balanced vertically, but it's moving to the right 420. In the case of, if this is the joint in a bridge, does it make sense? This is catastrophic. We don't want our bridges moving. Like, everything needs to stay static. That's what this course is about. We can't let stuff move. We're going to have to attach cables and pipes and, in order to stop things like this. And so that's kind of the backbone of what you're really trying to do. And that picture I showed you at the start about that roof on that house that I drew is kind of the key. It's not, physics makes this look really sterile, like there's, ropes connected to a hook or something like that. But it's like, where do these loads come from? It usually comes from something that has weight, and therefore it wants to fall. And you have it attached to a building in such a way, which means it doesn't want to fall straight down. Now it actually wants to pivot down. And so then you think, okay, well, it wants to do that. Well, how am I going to stop that? What am I going to do? In the case of the example I showed you, it's like, let's put a cable on there. But can you see how you have to determine that in order to hold this 500-pound weight, you're going to have a cable with a 653-pound tensile strength. And of course, you're not going to buy one that's 653. I don't know if you know this, but like for civil projects, which means lots of people are there, like a mall or a bridge or something like that, you have to double it. In other words, that cable would have to be, 1,300-pound tensile strength, because that allows some room for air. If the cable wasn't, built quite right, there's enough room for air in all of that you sort of can guarantee that it isn't actually gonna snap. So there's factors of safety built in. But of course, you got to be able to calc 653 in order then to make those kinds of decisions, because you don't want to waste money. You can't just put a huge cable in and hope for the best. I always think about this when I'm on ski patrol at Mount Ashland and I'm riding up the chairlift, and the whole chair, if you've ever been on a ski lift, the whole chair is hanging on this cable. It's about 1 inch in diameter. I'm just looking up at it, and there's all these skiers on it and wind, and it's been there since I was a kid. It opened in 1960, the same exact cable still sitting there. And I always just think, that would be fun if this broke, like, and all of this went down to the ground. And so it's not just, the cable came from the factory, but it's been sitting there for 50, 60 years now. Does it make sense? It's not as strong as it used to be. And so then that's what an engineer is trying to do. It's like, we need these chairs to stay static. We need to stay up above the ground on this thing in our life, as if you will, depending on it. So in a sense, before I learned anything about engineering, I'm sure hoping somebody did when they designed that cable. And I hope they even thought about, what happens 50 years from now? Is it still there? And, one of your jobs as an engineer is to go test things like that. They probably have to do that, test that cable in some way to see if it still has the tensile strength that's required, given the amount of time it's spent out in the snow and the cold and all that. This is simple, though. Like, do you agree? And what I'm trying to do is introduce this in a way that it's like the logic of this is not hard, but you got to know trig, and you got to be able to think and reason a little bit. So, and again, I'm inviting you not to raise your hand, so to speak, but coincidentally, Aaliyah's raising her hand, but just to interrupt, like, just start talking, because I'll be all busy and running along. So go, Aaliyah.
Okay. So on that last diagram that you were just drawing out, would the next step then be to figure out what you need to make the wall out of it, that it could take that much force from those places?
That's exactly right.
Would that be the next step?
That's exactly right. And that was my mistake for not finishing that. Daniel said earlier that you're going to need to have 3 of these because, and Ben said the same thing, you're going to need to have 3 of them because you're going to have to do something else to stop that sideways motion. So, again, it's a question with just arrows drawn on it. We still have some work to do, but in my case, let's say this was, let's draw this in a different color. Let's say this was the roof structure right there. And so again, even though it's this big rectangular roof, it's reduced to a 500-pound weight that is acting at its center of mass. And so that's the particle. It's been reduced to that particle. And so my figure shows that. And so if this is the building over here that it's against, does it make sense it's pushing into the building as a result of that? So if this is the building, then can we say, oh, good, there's a building there to stop it? Well, it depends what your building's made out of. Is it strong enough to stop that? That's not very much weight. 400 pounds is not that much weight in the world of engineering. And so most wood would stop that, no problem. But can you appreciate that's pushing into the wall? And so in my case, in that building, they made us beef up that wall. There was some huge kind of beams inside the wall that could take that force pushing into them. So in our case, it would just be, designing that. Or, with just the purple drawing, couldn't I come over here and attach one kind of going off the other direction, if you will, that would kind of pull back? Although if I attached in the other direction, does it make sense that both of these would have to work together to do the 500? Because if I just added this over here now, that might fix the 420, but then it screws up the 500. So in the end, we got to balance the horizontal and the vertical forces. And so as an engineer, you're going to be putting that stuff there yourself. But, for the sake of kind of the problems that you're doing in your assignment, they're going to be put there for you. And so let's take a look at this diagram now a little bit more carefully. Notice that this appears to be like a couple of pipes attached to the wall. And they're attached so that, I don't know if you can, we'll pay more attention to this later on, but notice that's kind of a hinge attachment. In other words, without the bottom one, that would actually kind of rotate, appears to be some kind of a hinge. And that might be good because when you take weight on and off, there's kind of a flexion to all of that. And so maybe you want it to move a little bit so it doesn't snap the welding joints and so forth. But anyway, that seems to be solidly attached to the wall over here, solidly attached to the wall over there. And so in a sense, this looks like some kind of a little crane system that, allows you to lift some weight, but it's away from the wall and so forth. But notice it's very contrived. This is, to keep it simple, when you're first learning this, it's a very contrived situation, but think of it as something that holds a sign perhaps away from the wall. And notice we're told here, and from chapter 1 that I hope you read, what do you notice about the weight? And they don't call it a weight, they call it a force. What do you notice about it? What's it say right there? What's it say right here? What's that?
500 newtons. So it's
Yeah, Newton. And that should not be new to you. You've taken physics. Should you be awesome at it? I don't know if you should be awesome at it. Anybody know what a Newton is? I know what a pound is, and that's because that's kind of, our standard system. And the chapter 1 talks about the US customary system, which is what you're used to, but then all the rest of the world does this in metric. And so all the rest of the world does not measure that weight in pounds. They measure it in newtons. So you'll have newtons and pounds. What's a newton?
Landon put it in the chat. It's a kilogram meter per second squared.
Yep.
So like on Earth, it'll just be 9.8 times how many kilograms the mass is.
Nice job. Interesting. He added a note that said, I know what Arecibo is. I've seen that before. That collapsed recently. Wow. And by the way, that's both the most interesting part of engineering is looking at failures. And I have some examples of that we'll look at. And I'm going to go hunt that one down, Landon. Thanks for mentioning that. But that's also where you learn things from. Like, you have to analyze why did that fail in order to learn what we know about engineering. It was based on failures. So yeah, kilogram meters per second squared. And I'll just say this regarding Newton's second law, which you should also have seen before, force equals mass times acceleration. It's a mass and an acceleration. So in the case of our weight, for instance, you have a weight of 180 pounds, but that's based on the acceleration of gravity based on the size of the ball of dirt you live on. If you live on a bigger ball of dirt like Neptune, then you're going to sort of weigh more on that planet because it's pulling gravitationally against you harder. And chapter 1 talks about that. But this is a huge formula. And the units of that, mass is measured in kilograms. And these units you need to know from physics and from chapter 1 in this book that I'm not talking about. And acceleration is measured in meters per second squared. And so this formula that Newton figured out, he figured out that force and acceleration are proportionate to each other, and that proportional constant is mass. An amazing formula. But notice the units of that, because of the formula, are kilogram meters per second squared. Well, that's a mouthful. You don't want to say something is 500 kilogram meters per second squared. So somebody makes up a name for it. Isn't Newton an appropriate name for that? Now that you understand the background a little bit, that's Newton's second law of motion. So let's come up with a new name for it. So you can just say 500 Newtons. But these units are going to be huge. And again, chapter 1 talks about this in terms of our ability to figure things out. So anyway, 500 Newtons of force is pulling down there. Now as a result of that, these two members, I guess we'll call them member AB and member AC, those are going to have to go to work. Do you agree with that now? In order for this to stay static, those are going to have to go to work. And you can probably picture that if this right here was a piece of string, then that's going to snap. That's not going to work. This is not going to stay static. That's going to bust in half. That's the idea here. But the question is how much work? See, your job as an engineer is to say, if somebody comes and says, I need this weird little structure here. And of course you can picture cranes. You've seen things driving around town, backhoes and things like this that are made of lattice work like this. But I need it to do this job. I need it to lift 500 Newtons. And so your job is to spec out what size pipe or cable goes there to do that. And this is complicated because do you see how they're working together? There's two forces here. And this is what Daniel mentioned earlier. It's going to take two forces to do this because we're not building this in such a way that something is pulling directly up. It's pulling off to the side. And so, you know, which one's got to work harder? There's a difference between tension, which is something wanting to pull apart, and compression, which is something wanting to kind of smash and bend and break in that way. And so ultimately we're going to have to know, we don't have to know that just yet, but we're going to have to know whether it's in tension or compression. And so does this feel complicated? It feels really complicated because how do I do this? Because if I look at this one over here, if I look at this top one and I think, okay, well, that'll pull back. Well, and I see what angles those are attached at. And so I can see that that's going to pull back, but it can't do all of the work. If I have it do all of the work, like a second ago, if this was kind of the 652 from a second ago, does it make sense? That's solving all of the 500 Newtons, but then this is either pulling or pushing. I'm not really sure which way. And that's contributing to the vertical component too. And so do you see how this is kind of confusing? How am I going to kind of figure out how much is left to each one of them? And the simple answer to that is what's easiest understood as vector addition, which again, you should have already touched in Math 112, which is trigonometry. You should have already played around with this a little bit. The idea is really this. If I have a particle or something that I'm pulling on and I sort of pull it in this direction, that's a 200, I don't even write down what it is, pounds. And then I head to tail, pull it in this direction, and that's longer. So that looks a little less than twice as long. So I'll say 350. And then third, I come back and pull it back to where it came from again. And that looks a hair shorter. So I'll call that 340. The fact that it went back to where it started basically means this thing is going to be static. Do you see the logic in that? In other words, the forces are pulling in such a way that head to tail, you can move vectors head to tail, that they're actually static. Now, let me show you how this might have been drawn in the original picture. If this was in the original picture, it might have looked like this. There's the 200, and I'm trying to redraw now that one up here. Actually, no, I think I'll just redraw it. I could copy it since I'm using kind of a cool program here. There's the 350, and this last one is kind of pulling off in that direction. So I'm going to try to copy that over there as well. That's not too bad. I guess I can live with that. That's the 340. Does it make sense? This is exactly the same drawing, and that particle or that point is actually static. So a vector is kind of like the wind in the sense that you can move it to wherever you want it to be. So the original problem might look like this. Now your job as an engineer might be, how strong does that cable need to be so that this thing actually stays static, given that it's being pulled at 200 in one direction and 350 in the other? Then, you know, where do I put that, and how strong is that last one to actually keep this thing static. And your ability to do that is going to be based on redrawing this head to tail. So vectors can move. And the cool thing about that is, would you agree that that triangle that the head to tail version created is a non-right triangle? And you knew, I should say, the law of sines and the law of cosine, so you don't have to have the right triangles to pull this off. And so let's see if we can apply that logic to this question that is in front of us now in green. So all I know for sure then, if I kind of redraw that down here, is that I've got .500 newtons pulling down. And the key is I need to get these other two vectors. And I don't know which way the arrow is drawn, but I need to get it back to the start, kind of back to where it came from. So let's see, they're in order A, B. So here's A, B. So how do I do this? Where do I attach this? Well, I'm going to try, and I'm actually going to see if I can copy that. I'm going to take this down here and actually attach it head to tail. So based on the way that I attach this, does it make sense that I'm kind of drawing it in that direction, I guess, if you will? In other words, I'm trying to get it to go back to the start. It's going to have to go in that direction, because the only way that that pipe can work is in its direction of orientation. It can only either pull or push in that direction. And then the other one, which I'll draw in blue, only goes in the other direction. So that's no good, because you agree that's not going back to the start? What's the problem here?
Well, our forces are too big, so we need to, yeah, depending on what our 500 scale is originally, we need to have the vectors at smaller scale so that we'll hit that point.
Yeah, keep in mind those links that I just used, those are the links of the pipe, not the strength of the force. So the length of the vector represents how strong the force is. So when I drew 500 a second ago, does it make sense that I just drew a line? I didn't know how long to draw it. So apparently what this is telling me is that my 500 really should be quite a bit longer than it is. It doesn't matter what size I draw all of this, it just matters relative to each other. But notice, because I copied it, good. Let's see, let's switch this one to purple. Because I copied 500 over, I don't really know how long to draw it. But notice this drawing is pretty accurate now. So notice it's kind of the same as the original picture, but now these vectors are all drawn head to tail. And so if this purple one represents 500, then can you guess at the size of the other two? Well, that looks shorter. Doesn't it look shorter, but not way shorter? It's not 200. What do you think? 400? Does 400 look reasonable? What about the blue one? It looks shorter still. Does it look half of the purple or more than half of the purple, would you say? Because the purple one's the only one I have to gauge off of. I'm going to call on you, but clearly it looks more than half. So maybe, I don't know, maybe I'll say 300. I don't know. But the question is, could we actually figure them out, not just have to guess? Who's got some ideas? How am I going to figure that out? I got this triangle that I've made by drawing these things head to tail, and it really does finish where it started if I draw these things the right length, if you will.
Can we just set one of the anchor points as like 0, 0 and balance out all the torques?
Yep, there's a number of ways to do this. One of them is with two equations, two unknowns, which is actually the easier way, and we'll get to that later, which is kind of what you're getting at, Daniel. But the other one is just to treat it as it's a triangle, and all I have to know in this triangle, I know, I guess I'll erase those. In this triangle, I know one side is 500, and I know the angles. Well, I don't know the angles, but I know something about angles based on this picture up here. Now you got to be kind of careful. Can I put 30 or 45 down there somewhere? I mean, I see the original has got a 30 and a 45 in it. How do I get those into the picture? Here's where you got to be careful. Let's see. I'm going to choose black, I guess. There's not a set way to do this. You just got to be creative. What's your idea, Leah?
Since below the blue, A to C is 30 degrees. And I believe the other one below A to B was 45. We can take the opposite side of, we'll just say green, and add it to that 30. That's in the bottom triangle. It'll be the angle to the right.
So you're seeing
in between
something.
the blue and the green.
I'm going to draw some things in, like in that picture up above, it was this that was the 40-degree angle, right?
45.
You are correct. It's too small. And 30, so. And it was this that was 30 degrees, right?
Yep.
So what's your idea now that I drew that in, to let everybody else have a chance to think about it? Because you're right. I think I know what you were getting at, but
Did you want someone else to answer
I
or
don't
me?
care.
Okay.
Go for it.
Hmm?
Yeah, Leah, go for it.
Okay. Since it's a 90-degree angle between the horizontal and the vertical,
Yeah.
and we know that this part is 45, the other part of that would also be 45, because
Yeah.
90 minus 45 is 45.
The
And
two
then we
black
can add
lines
that
are
to the
horizontal
30.
and vertical. She's exactly right. So that makes that 45, which means I now know one of the angles in there. It's actually 75. So there's no rote. I can't just say whatever angles you see, add them together, and that'll be one of the angles. Sometimes you're subtracting them. You got to be really careful. Draw the pictures in. That's not enough. I know one angle in the triangle, 75 degrees, and I know one side, but I need to know another side, which I don't know, or I need another angle. So what other angle could I know?
Is a purple line is like straight down, right?
Yep, purple line straight down.
So there's an angle whereas the purple and green is going to be 45 as well.
That's right. So if I continue this across, then that's 90 degrees since the purple straight up and down, which means I know this angle is 45. And for the same reason, I actually know the one on the top would be 60. So it's 60, 45, and 75. So I know all the angles in that triangle. And now I could do law of sines to figure out what the length, and again, I'm saying length because they're not really lengths, but that's what's cool about vectors is that the length of the vector is the force. So I'm not drawing this as a length triangle, I'm drawing it as like a force triangle. So now I could say something like the sine of 75 divided by the side across from it is the same as the sine of any other angle. I'll do 60, I guess. I'll switch to green since it was green. So I could say it is the sine of 60 divided by, well, what are we going to call that thing? That green vector was actually vector AB. So I'm going to call it force AB. One of the things you got to get better at, I don't know if you're kind of, I'm sometimes lazy about stuff I write down when I'm just speaking to myself, but one of the things you got to start slowing down on is having good notation. And what I'm going to do is not tell you exactly what to write, but you got to do something here to say this. Now you could do creative things, like you could come back up here and say, this is vector 1 and this is vector 2, you know, something like that. I don't really care what you write. What you'll see, what you would see if you looked at the answers in the book would be something about A and B, like maybe what I wrote, but it makes sense to say force AB just because in the picture that was AB. So I'm going to write here, even though it's a little cumbersome to write down, I'm going to say force AB. And you've had a lot of math, so I have to assume you can do this no problem. So I end up taking the sine of 60, just doing the algebra in my head, times 500 divided by the sine of 75. And I do that, I get 448. Did you read chapter 1? What am I going to see in the back of the book for this answer? What I got was that force AB was equal to, and because of sine, I'm going to get a crazy answer to this, 448.2877, and I'm going to stop because I'm out of screen right there. What are you going to see in the back of the book? What is the standard rounding that this book in chapter 1 says as far as how this is going to be rounded?
It said 3 significant figures.
3, round it to 3. Now in this case, we're sort of lucky, it's 448. If this answer had been 448,287,000 or something really large like that, how are you going to write down a 6-digit number with only 3 numbers? And so we'll talk about that when it comes up. But the back of the book is going to say 448 newtons is close enough for the force of AB. And for the sake of me grading your stuff, it's very good practice to do what I just did, which is draw someone's attention. There's a bunch of calculations, blah, 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 but you know, there's the answer. And if you don't call this force of AB, did you call it something that I'm going to recognize? Can you call them force 1 and force 2? Sure, as long as the original figure has something that designates one of them as force 1 and one of them as force 2. So if you don't like the AB thing and whatever, but box an answer to draw my attention to it, to draw your attention to it. It's like mission accomplished, it's finished. I think I erased my original guess, but doesn't that look reasonable? Why does it look reasonable? This is more important than the calculations to me. Does it look reasonable? Why does it look reasonable? Somebody chime in.
Well, it's almost 500, so it's,
Yeah.
it seems like it should be, it has to be less than 500 because it's not a hypotenuse, but it seems like it's pretty close to that.
Yeah, because I was very careful, and a lot of times in this class, if you've never done this before, you might want to consider starting to draw your figures with a ruler. Like, don't sketch them all ugly style like I did here. Draw it with a ruler and actually measure out 45 degrees and measure out 30 degrees and so forth. If you do that, in my case, I stole the lengths directly off the previous figure, so my drawing is actually pretty good. And so the green vector is clearly a little bit shorter than 500, and therefore my answer of 448 makes total sense. So I could also say, while I'm at it then, just to finish this, that would be the same as the sine of 45 divided by the force of probably BC. Force of BC. So if I calc that out, and saving a little bit of time, all I have to really do in this is go back and change the 60 in my calculator, change that to 45, and I get 366. So, and in this class, you're certainly not done unless if you don't have newtons on there, you probably were picked on this by Dusty in physics quite a bit as well. But this is a place where I think you can understand that units are essential. This isn't just somebody, being mean, like it feels like in maybe a regular math class. But if you just say 366, you're a long way from done. Because you've got to, because in the real world now, you can't just say, hey, look, I've calculated it. You have to go now pick pieces of steel that can do that. Does that make sense? And so That's pretty cool that you're able to calc. And what we're saying here is that because those vectors are head to tail producing a triangle that collectively causes the force to affect, and then think of this as just somebody pulling. Somebody pulls it this way, and then somebody pulls it back that way, and somebody pulls it back that way. Hey, look, it's back where it started from again. That, because it's head to tail and created a closed triangle, because there's only 3 of them, that means all these forces are actually balancing vertically and horizontally. And we won't take the time to do it, but I would encourage you to. You could actually go back and see what is the vertical component of the blue and the green and the purple. If you add all those vertical components together, notice the purple is down, so that'd be negative 500, and the green is up and the blue is up. And so those would both be positive. And so the vertical component of the green plus the blue is going to be 500 because that balanced it vertically. What do you think is going to happen with the horizontal components of the blue and the green, since the purple didn't have a horizontal component? What's going to be true about the horizontal components of the blue and the green?
They're going to add up to 0.
Yeah, they're going to be equal because one is pushing to the right. So for instance, if the green component to the right was say 300, then the blue component to the left is also going to be 300. So therefore they balance. And so that's the math behind what's actually going to make this shape static. And it's your job to choose the pipes that do that. Now, again, notice we haven't talked about, are they under tension or under compression? Because that matters. You can use a cable when something's under tension, but cables are floppy, and so they're not going to do anything under compression. Concrete is awesome under compression, but it's terrible under tension because it just tears apart. So you have all kinds of materials to consider. So you're going to have to go back as an engineer and then say, what materials are you going to use, and sort of guarantee that it'll do its job. So you can actually do the math. You don't just have to hang the weight from it and go, it worked. That's cool. I was lucky. What's your thoughts on that? How's your brain?
I was going to ask, just like I said, and I think you're kind of saying we'll talk about this more later, but like, how would you know, how would you push or pull, how would you differentiate between, how would you, cause something to push on it rather than pulling on it?
Yeah. We are going to talk about that later. And it's kind of a can of worms a little bit.
Okay.
So I can't completely address it right now, but I'm glad you appreciate the fact that makes a difference. Maybe you can tell by looking intuition wise, if you came over here and you hung this weight and you pulled down on this, is that going to make the blue pipe want to get shorter compression, or is it going to try to pull it apart tension? Can you tell just by looking at it?
Yeah, it would compress it.
That's right. It's pulling down, it's going to compress it. So actually blue's in compression, which means it would need to be a pipe or something that can withstand compression. What's going to happen to the green? If you pull down right here, is the green pulled in tension, or is it smashed in compression? You can see it in this shape, can't you?
Yeah.
So actually AB is going to be under tension. So I could actually use a cable there, which is exactly what I used on that house drawing that I showed you a minute ago. And the blue one would actually be under compression, but it's going to get more complicated than this. You can't always tell, and it's not always obvious. And truss structures and roofs and things have pipes going everywhere, and so it's sometimes it's counterintuitive.
So then, in our diagram, if we were being accurate, we might have we have done it the other way, so that the blue arrow was going the other way, and the green arrow was.
No, because in the end, there's 2 arrows. In other words, if you're under compression, let's think the walls are coming in on me. The walls are coming in. Does it make sense? I'm pushing out both ways.
Oh yeah, it has to push out.
There's actually arrows on both ends.
Okay.
And so that's what we'll talk about kind of later on. So what we're doing is just figuring out how much force is on it, but we're not talking about, kind of what direction is it going. And incidentally, how did I know to do, let me just quickly draw this over here just as a side note. How did I know to attach the green vector first? Could I have attached the blue vector first? Did I get lucky? The answer is, doesn't make any difference. notice that blue vector is the same as this blue vector over here. I'm just trying to draw them parallel to each other. You can tell it's not perfect. It's a little too short, right? But if you attach that first, then you'd come back and the green would have taken us back to the start. You get the exact same triangle. So we sort of said green person pulls second, blue person pulls third. If you do blue person pulls second and then green person pulls third, you still get back to the same spot. So there's more than one way to kind of visualize this. And you would have got all the same answers had you done that. Let's take a look at another problem. I will say too that this is a 3-credit class. So we're meeting for an hour and a half, 2 days a week, but it's very hard to get this done. It's very hard to get this done in an hour and a half every day because there's just so much stuff to think about and we need more time. There you are. So I'm gonna give you a second to stare at this. And again, one of the things I like about this Hibbler book, and I'm usually hate textbooks, but oddly, this is one of the few that I've ever thought, wow, and I mean, talking in 30 years of education, this is actually good. Like his drawings are awesome. Like, can you see what that is? Can you tell that that's, I mean, he's actually taken the trouble to draw bolts into it. And you have, and maybe you can picture this as like a chunk off of a bridge where you have a plate. And so you say, all right, let's get this member coming down here to attach. Well, we just drew pictures of things being attached. Well, notice he actually drew the attachment in. There's like this metal flange that's attached and bolted through to the original structure. And then you have your pipe over here, which is bolted into that flange. And so it kind of actually shows the connections. Can you appreciate if 8 newtons pulled hard enough that both of these bolts, what's called sheared in half, which basically means the bolt just goes in this direction, the 8 newtons could be strong enough that those bolts would just rip in half. That's called shear. We'll get to that later on. But that's one of the things an engineer's got to do. How many bolts? Is 2 enough? Well, sure. If they're thick enough, can you get away with 1? Yeah. If it was bigger, can you do 3? Sure. Then they could be smaller. Can you do 10? Yeah. I mean, those are all choices you make as an engineer when you're designing something. And so, the plate's subjected to 2 forces at A and B. And so this force is pulling up at 8. What's that little K? Again, you should already know this because you read chapter 1. That's not 8 newtons. What is that?
8 kilonewtons.
Kilonewtons. So that's actually 8,000 newtons. And that's one of the things that's, notice the number 8,000 is a 4-digit number. So what you try to do in engineering, and it makes a lot of sense, is not have numbers. You've done this, right? You have a number that's like 7 numbers long and you accidentally write it down wrong. Like you can't afford those kind of mistakes as an engineer. So it's like, let's have 3 numbers or less. So how are you going to write the number 8,000 when it's a 4-digit number is only a 3-digit number or less? Well, 8 with the prefix kilonewtons. So the K is taking care of the 1,000. If this was 8 million newtons, does anybody know what the designation would be? 8 million is a 6-digit number, 7-digit number. What's the prefix? And you got to look at chapter 1 because I'm not teaching this, but it's just going to come up here and there. Million is mega. There'd be an M in front of it. 8 MN, 8 meganewtons. And you can appreciate that would not be good to get wrong. I mean, you're designing a bridge and oops, I thought it was 8 newtons. Sorry. I mean, you gotta know this stuff.
Also,
Go ahead.
mega would be a capital M because
Yep.
milli is a lowercase m.
Nice job. Yeah. From physics, the little m is millinewtons, like a teeny force. So the M is capital. And so there's just a lot of things you could screw up here. So, well, this seems like there's no way this could be in equilibrium because aren't they both pulling to the right? There's no way this could be imbalanced. But what is it asking us to do? The plate's subjected to 2 forces and one of them shown at 60 degrees. They're telling us theta is actually 60 degrees. And so maybe they're reusing this in the book for 2 different problems because they're actually telling us that's 60 degrees. Determine the magnitude of the resultant of these 2 forces and its direction. In other words, they're saying this is moving. Like, what's the result of both of these moving? Does it make sense if you have both of these pulling? As an engineer, you need to know what's going to happen. Now, you surely can tell the result is these are going to want to go to the right because they're obviously both pulling right. But do you think the net result vertically is actually horizontally vertical or negative? Is it up or is it down? Well, 8's bigger than 6, so wouldn't that make it up? But not necessarily, because 8 is pulling at a lower angle. Does that make sense? And so it's kind of up in the air. I'm not really sure exactly how that might work. So in a sense, what we're doing is thinking of this is, go ahead, Aaliyah.
Is magnitude the force and direction?
Nice. Good job. Magnitude is both force and direction. And you can appreciate I need both, right? I need to know how strong and I need to know what direction it's going. So thank you for pointing that out. And thanks for interrupting and not raising your hand. Good job. So there's a couple of things I could do with this. Let me see. I think I'll do it the hard way again. One more time. So I don't know, for no particular reason. And notice this time they didn't call it A, B. It's just like vector A and vector B or something, and that's good. So there's force A and force B. That's a little cleaner to write down. So I'm purposely going to kind of go over here and try to copy. And I'm just eyeballing this. I'm going to try to copy force A at 8 kilonewtons. And again, does it make sense I could bust out a protractor if I wanted this to be really accurate? But at least I stared at it a little bit. And so there's A. And now B takes off. And notice I'm redrawing them again as head to tail. So now I'm taking off here in the direction of B. And so let's see, how does this do? I have one luxury you don't have, and that is I'm drawing something I can let it move. How long do I draw this? Do I just draw it any length I want? I drew green any length I want. How long do I draw this? Blurt it out. I don't mean you know, but what is it I'm thinking?
It's gonna be 6,000, so it's gotta be less than green.
Yeah, the green was 8 and this is 6, so I've got to draw it shorter than
It's
that.
gonna be
It doesn't have to
3/4.
perfect, but good job. To be really accurate, to be 3/4. Could you bust out a ruler and actually draw the first one, say 8 centimeters long, and draw the second one 6 centimeters long, or 8 inches and 6 inches, or 4 centimeters and 3 centimeters? Yeah, that'd be awesome. If you actually busted out your ruler and did all that, that'd be fantastic. So I'm just going to eyeball it for now. And so that is B. And so does it make sense this did not return to the start? There's only 2 things pulling on this. There's 2 vectors that did not return to the start. This thing is moving. Well, does it make sense to you then that this is the resultant? Collectively, that's where that's going to go. If one person pulled this in this direction and then somebody else came and pulled it there, wouldn't you say the net result of that is it just got pulled across there? So if these are pulling simultaneously, that's where it's going to go. Now, did I draw it accurately? Probably not. I just kind of guessed, but notice it's down. Like overall, it's actually being pulled down, mostly to the right and a little bit down. Remind me to show you this in AutoCAD in just a second. I hope I don't forget this, but I want to show you how you can actually, if you draw it accurately, like with a ruler, you could actually just cheat to get the answer. I'll show you what I mean. Well, again, I have this triangle now. So this time, notice the arrow though it isn't drawn the other direction. Like this is a resultant because it wasn't in equilibrium. It wasn't static. So the arrowhead is purposely drawn, well, head to tail. It's like drawn from the tail where A started over to the head where B finished. But it's still a triangle. And so again, I have the same problem I had last time, which is somehow I got to take that 60 and 40 degrees and I've got to get them into that picture. And I don't know, like as I'm sitting here right now, I don't know what the answer to that is. So what I'm going to do is just try to get them into the picture. So since 60 is vertical, then I know that angle is 60. And notice by itself, that doesn't help me. The blue is not horizontal. So you cannot come here and say that's 30. Do you understand that? It's not horizontal. I don't know that. If you do that, you're going to get it wrong. So that 60 doesn't, it's almost like it doesn't help me. That's not good. And then 40 degrees is from vertical. See, vertical to where that thing goes. So I could come over here, I guess, and put that in. And that's 40 degrees. And so I'm kind of in trouble because that 40 is not the entire angle and 60 is like not helpful. Who knows their geometry well enough to get us out of this mess? Also, do you understand that this does not hit at 90 degrees down there? Again, blue would have to be horizontal for that. Doesn't hit at 90, so that isn't helpful. This angle over here is not 50 degrees. We're in a sense unlucky that that blue line is so close to horizontal because that might fool us. Well, you got to be a little better at geometry. Would you agree? And actually, I still don't know. I'm thinking out loud right now, and I purposely try not to prep too much for these questions so that I can think out loud. But here's something I know about geometry. If this one is vertical and this one is vertical and that angle is 60, then I know this angle up here is 120 because those have to add up to 180 degrees. It's kind of like about face. In other words, this is coming down and it goes back, turn 60, turn 120. Now you're coming back parallel to each other. Another way you could know that wouldn't be quite as tough is to say, well, aren't these two angles going to be the same? Like if that's 60, isn't that also going to be 60? That's easier. Does that help me at all?
Without even those angles, couldn't we just break them into x and y components? So we'd have the x component in this case for vector A being whatever the cosine of 30 degrees is. The y component would be the cosine of be the sine of 30 degrees. Then we do the same thing with B, add them all together, and we get another vector in component form, which we can then convert into an angle and shit.
At the start of this, I said, I was trying to decide which way to do it. Let's do it the hard way. I said, what Daniel's pointing out, and I may even get to that today with this question if we have time, but we could actually break the green vector into its horizontal and vertical components right now, and the blue and the red one into its horizontal and vertical, and then just consider them totally separately. And that's actually easier. And that's generally the method we'll use this whole class. So absolutely, Daniel, that is easier and you're onto something there. But notice because this angle up here is 60, that the one directly across from it is also 60. Since this is a straight line and this is a straight line, then those two angles are 60 degrees. Those two angles are going to be the same exact angle. So 60 got into this triangle. But notice it's not one of the angles in the triangle, but now I got 60 and 40. So I know that angle is actually 110 now. So I know one of the angles. Is that helpful? I'm going to try to make a rough re-sketch of this. So this is 110. What else do I know about that triangle?
It'd be 100, right?
It should just
100.
just be 100.
Just kidding. Does that make you feel a little worried that your teacher can't add? How's he going to teach us all this stuff if he can't add? I'd be worried. What else do we know about that triangle? We know both of those forces. Remember last time we didn't know very many forces, but this time we know both of these. We know that this one was 8 kilonewtons and this one is 6 kilonewtons. I don't know if you're good enough at trig to understand this, but hey, I know 3 things. I'm on my way. I don't know to know any more angles. Maybe I could know more angles. Maybe I couldn't. I'm not sure. But as soon as I know 3 things about a triangle, 2 sides and an angle. Last time we knew 2 angles and a side. If you know 2 angles, you always know the third. But again, now I'm on my way and I can start figuring stuff out about this triangle. Are you still good enough at trig? Is this a law of sines or a law of cosines problem? Let's see, how am I going to do this? Let me waste just 1 second here. Where are you? Examine test notes, share. I'm not, and of course you can probably appreciate that as an engineer, you don't need to have stuff memorized. Like you got books, you got the internet, you can look things up. So this is we're going to kind of create together. I mean, I've taught this class more than once, so I already have one together, but we're going to kind of create the notes for this class as we go. But, you know, I don't expect you to have memorized the formulas that we're going to use in this class. And so here's the law of sines. There's a picture over there. You probably remember seeing that in Math 112. Here's the law of cosines for a picture over here. Notice little c length is across from big C angle. Little b length is across from big B angle. And so in this case, basically the law of sines does not work unless one of your angles is across from one of your sides. Does that ring a bell from Math 112? And so we're going to have to use law of cosines. So I'm just going to kind of write that out and use it, but I'll post that so that you have access to it here soon. So let's see, I called that R over there. I'm going to call it force R since these are numbers, since 6 kilonewtons is a force, I'm not just going to call that R. I'm going to call it force R, just to tell myself and anybody else that that's not a length, it's actually a force. So now I could write out the law of cosines, which would say that, let's see, the key thing in the law of cosines is that of the 3 sides that I now have names for, 8, 6, and F, the one that's by itself is the one that's across from 100. So I could say that the law of cosines tells us that force R squared equals 6 squared plus 8 squared. That looks like the Pythagorean theorem. But notice that's a 100-degree angle. It's not a 90. This is not a right triangle. You can't use Pythagorean theorem. Minus, and this is the part that law of cosines adds, minus 2 times A times B times the cosine of the angle that's across from this. That's why I chose to put FR over there. Great. That's actually not hard. All I have to do is simplify the right side, take the square root of it, and I know force R. Based on the picture, to me, it looks like that blue vector is longer than the other two. So I'm thinking it's actually going to be a little more than 8, like maybe 9. But again, I'm a little worried because I didn't draw my picture. I didn't copy this off the sheet. I didn't measure 6 and 8. I just kind of eyeballed it. So let's see. So when I do that, I get that FR is 10.8013 and goes on from there, 99 and so forth. What is that? Well, and again, this is why I called it not R, but FR, because that's a force. And because the other ones were labeled kilonewtons, this is labeled kilonewtons. And I was right. It is my blue vector was a little longer than my green one. And I thought it was going to be more like 9, but it's 10. And not only that, it's close to 11, which kind of tells me my drawing is probably a little off. So force of R, I could say, is 10.8. It would be important to say kilonewtons to that. It'd be important to box it to tell myself and everybody else. There's the answer. What is that? What was this problem asking us? It was asking us for the magnitude of the resultant of these two forces and its direction. What did I just find? I need the magnitude and the direction. Well, I just found its magnitude. Magnitude and, so if it had just said determine the resultant, then I would need, that's kind of the magnitude and, But it goes on to say, and its direction. And then notice it's like its direction, but it's kind of unclear about, what that means. And so I found the magnitude. I'll just kind of make myself a note there that that's the magnitude. Make you a note, because again, I'm posting this stuff. So collectively, those are both pulling. And can you, if you go back to the picture now, does it make sense that since that's what's happening here, that I guess these bolts, notice there's 6 of them there, those bolts better be strong enough to handle, well, 11,000 newtons of force. Hopefully those bolts don't tear apart at 11,000. That'll be your job as an engineer to make sure that happens. In that case, those bolts inside there will be under tension. So, is 6 of them enough? Is 6 enough if you use a certain kind of steel? Depends what kind of steel you use. So that's why we're doing this. We're not just calculating it to calculate it. That's one of the things the book kind of leaves out. How am I going to get the angle of this? Well, actually, you tell me.
Well, we can use law of sines now because we now have a pair of an angle and a side to compare to the other sides, and then we can figure out what the other.
Again, you got to be a little careful about rounding here. Notice I may be rounding that too much. If I wanted to be really careful, I'm not going to ding you for this in a book, in your tests and so forth. But if that had been sent like 10.84, for instance, I might have wanted to leave the 4 there. Since it's 10.80, I'm just going to call it 10.8. But you might miss the answer in the back of the book by like 0.1 degrees or something because you rounded that too much. Just because the written down answer is 3 significant digits, 108, 3 numbers are written there. Remember, what that really means is 10,800. But I think I can get away with that round here. And so what Ben said is true. Now I could switch to law of cosines. I could say the sine of 100 divided by the side across from it is the same as the sine of, I don't know, I think I'll pick that one. Theta divided by the side across from it. So again, you should feel pretty comfortable with solving that. And if you do, you get that angle is about 33.1645 degrees. What are you going to see in the back of the book? What's the back of the book going to say? If you got this right. 3 digits, 33.2. If you say on a test 33.16, are you wrong? No. If you call it 33 degrees on a test, are you wrong? No. But understand, this book is saying 3 significant, and that's a good decision, right? At 30, call it 33.2. That's a good place to round this. That's smart. It's a little more accurate than just 33 degrees, but who needs it to be that much more accurate? So is this the answer? Box it. Well, 33.2. Is that the answer? No. Because that is 33.2, but it's 33.2 measured from vector A. Does that make sense? And that's the problem with angles, is like, what is this measured from? Notice they were kind of careful up here to say measured clockwise from the horizontal. In other words, you can't just list an angle, otherwise nobody even knows what you're talking about. You got to have a picture somehow. You got to have something that shows what the heck you mean. So that is not the answer. And it does make sense not to give the answer. Now, it would be the answer if you said measured from force A, but does it make sense that wouldn't be that helpful? Because it's kind of like, well, where's force A? If you included a bunch of angles. But what I need is, the smart thing to do here, even without what they said, is to say, what is it measured from, horizontal? Isn't that what we called 0 in trigonometry? So the entire angle over there is 33 degrees, but it makes more sense to say that that's actually down, I don't know, what is it, 2 degrees? I'm not sure. How am I going to figure that out? How am I going to know what that is? Well, here's where your previous figure kind of helps out. That 60-degree angle up there, how does that help us now? If I come back here and put that 60-degree angle in, does it make sense that angle right there is 90 because the red is vertical and the red is horizontal? So I know that's 90. So then if that's 60, then that means this is 30 because that's 90 now, right? And then the angle, the theta angle was 33.2. So that means this angle right here is actually 3.2 degrees.
But then wouldn't you put it back out to 0.16?
Right.
For your final answer, you need 3.
Exactly right. So in the back of the book, if you said 3.2, the back of the book might say 3.16. As far as I'm concerned, don't change it. Like if you see that in the back of the book, go, oh, that's right, I forgot. It's supposed to be 3 digits. Don't even rewrite it. But it's good practice to do that. So that's exactly right. Now let's see. They were very specific. Now, one of the things you could do, like if you were going to answer this on a test, you can't just say 3.2 degrees. That doesn't help either unless you have a picture. Do you understand that? And you can't say 3.2 degrees from horizontal because that could mean 3.2 degrees this way or that way. Now in this case, they told us a very clear description, measured clockwise from horizontal. So here's horizontal and I turned clockwise. And so because they gave that full description, then I could just say 3.2 degrees and I'm okay because the description gave that. It would probably be better if you just drew a picture of that, because I mean, that's a lot of words. So to say, to draw this as horizontal, and then to draw that down and write 3.2 degrees right there, and have that be your answer, that's probably better. Like a picture is worth more than words. I can see somebody getting screwed up on clockwise and counterclockwise. It's kind of a dud, but they're not going to screw it up now because I have my picture clearly drawn, right? And notice now we know it's really down. Does it also make sense that without saying clockwise from horizontal, you could call that negative 3.2 degrees? I'd be okay too. And so, I don't care. Like, I'll understand what you mean, but you got to make sure you communicate. 3.2 is not an okay answer without the description that they gave up here to go with it. And so now I know the magnitude and the direction. And as Aaliyah pointed out, I should say 3.16. So this is the direction. And so armed with that knowledge, does it make sense that you would sort of know what you collectively took both of those forces that are kind of complicated and you put them together, and now you know kind of what's happening at that plate level, and so now you can make sure the bolts can handle that. Notice there's a little bit of force downward now, so that means the bolts might want to shear off. Okay, let me show you something kind of cool. By the way, I'd say most days I'm probably going to go till 12:30 in here. I'm going to try to quit it at 12:20, but I always end up, because there's too much in this class, I always end up needing a little bit more time. If you need to leave, then split. Like, you don't have to say I got to go, just leave. And I'm going to try to not say things you really need to know during that time period, but I'll do the best I can. But what I won't do is keep you for like 40 minutes late. I begged them to make this a 4-credit class, so we had 2 hours, but okay, watch this. So I'm drawing in AutoCAD right now, and I'm drawing force A. And from the vertical, that was 60 degrees down, correct? Now, your AutoCAD is kind of cool in that it calls 0 exactly what you think it should be called from trig, which is to the right. So if I type in right now, I want to go angle of 30. Do you see how it sticks at the correct angle? So I've limited it to say I only want to go 30. And then that was 8 kilonewtons long, right? So I'm just going to say 8. Now, just so that you can check to see that worked, if I draw a vertical line in here and I go in here and dimension this, Notice that's 60 degrees. It's working, okay? And then we took off from there. I forgot, what was the other one? 40 degrees. It was 40 degrees from here, right? So from down here, I need to go up 40 degrees. Well, does it make sense from here? That would be down 50 degrees. So if I want to go down 50, how do you say that in trig? How do you say down 50, not up 50? Remember, positive is this direction. So I could say negative. I could say negative 50 degrees. And that I wanted to go 6. So again, let's just check and be sure that that worked. Is that angle that they gave me in the sheet actually 40 degrees? Yes, it is. Okay, good. I didn't screw that up. And so would you agree this line right here is the resultant? Would you also agree that I just drew that perfectly? Well, here's where AutoCAD is cool, because the drawing is perfect. How long is that line right there? Isn't that the math we just did a second ago? Like all the trouble we just went to? Like engineers are not going to do what we just did to calculate this stuff, because you have machines that can draw this kind of stuff. And you know, even though I know what I'm doing, like you can make a math mistake. Can you get the angle? Sure. If I go in here and draw a horizontal line and I go up here to dimension and say, what size is that angle right there? Notice it says 3. I have it set rounded to the whole number right now, so that's why you don't see the rest of it. But it's like, hey, look, 2 seconds, I'm done. That's kind of cool. So that's the power of vectors. Do you understand? Like if you draw the lengths correct, if you actually draw the lengths to scale, and you did this with a ruler. Now you would, with a ruler, you're not going to be as accurate. You wouldn't be able to get the right answer from a ruler, but you could actually check your work. If you got 3 degrees, you could kind of measure. And if it was within a degree or two, you'd probably know, probably get it right. Or the length, I could draw those pretty close to accurate with a ruler and a protractor. And so if you got something around 11, then you kind of know, cool. You could measure it and see. That's kind of cool. I guess because of time, I can't show you Daniel's much simpler idea, which is to break these into horizontal and vertical components. But you can just take that, and I'll just leave it at this for now, and we'll pick it up tomorrow. But you can take that 8 kilonewtons and figure out, well, how much of that 8's horizontal? And how much of it is vertical? And then I could take that 6 and do the exact same thing. And then I can compare them separately. I could just take the two, the horizontal version of A. I got to go back so you can see this quickly, and I'll shut up. I could take the horizontal version of A and the horizontal version of B, and does it make sense? I could add those two together and I would know the horizontal answer. And I could take the vertical version of A, which is going up, and the vertical version of B, which is going down, and one going down would be negative and going up would be positive. And I could get the combination of the vertical component, and in the end, because of the math we just did, it's going to be a small downward answer. And so then I would have the horizontal and the vertical, and then I could do Pythagorean theorem on those to figure out the actual angled length. So I guess we'll just wait till we can do that later. I'd like to do it right now, but I don't want to make you stay. So okay, let's call it good for now. So I'm going to go post these physical notes. I'm going to go post the lecture that I just gave at My Open Math. Stay after class right now. If you want to ask me any questions every day after this class is over, you can just stay here. I just want to make sure people have permission to leave, but you can ask me questions about My Open Math, or, you know, whether you're in the class or something that went on today. Otherwise, see you tomorrow.
Yeah, I couldn't get into My Open Math with the password and the key you gave me. I tried, saw 2 different ones, and I Both times it said it was incorrect, so I don't know. I put it in
Pull
wrong
up,
or something.
Let me pull up the syllabus for this class. And I'm a little worried that I went into Blackboard and like I changed this. And so the syllabus that I just sent recently,
Yeah, because I think it was different on Blackboard and on the syllabus.
yeah, do this right now while we're sitting here. I think what I did is I changed the enrollment key to say winter 2021, but then I forgot to go back to Blackboard and repost the new syllabus. So the syllabus I sent you,
No,
is
okay.
right, but I think the one, so try to get in there right now while we're sitting there.
Okay.
Doug,
Go ahead, Ian.
my when I click on the link to My Open Math, it just brings me to the display screen showing like your previous like Math 251 and Math 252, but it doesn't give me, I'm not sure how I join your class. It just brings me back to My Labs, like My Labs Plus, showing it the other classes I've been in previously when I click on the link in the syllabus.
Go to add a new course. I'm not
Yeah,
exactly.
where does it say that to add a new course?
I'm not exactly sure what you see. So let me.
It worked for me, so.
So yeah, Stan, maybe you can help us through this if he's not seeing what I see. When I go into My Open Math, I think you see what I see, which is, these are all the classes I'm teaching, and I know I have different access than you do as an instructor, but the main thing is to go right here and say add new course.
Oh, I'm on a completely different website. I'm on like Pearson My Labs Plus whenever I click on that link in the syllabus for some reason.
The sheet that I sent you is for My Open Math, which is not the same as My Labs Plus. I was wondering if that was the case.
That's so weird because it takes me to that when I click on the link in the syllabus. It takes me to My Labs Plus.
The link in the syllabus. Let me see. Where did I send you? Did I blow it?
Yeah, the link says roguecc.mylabsplus.com. Okay.
That's not good. This link. Oh, wow.
Yeah, that link.
Yeah, that does say mylabsplus.com. That's not good. Why is it? Wow. All I did was type that. Why in the world
That's
did
weird.
that show up? Yeah, just
What would be my login for My Open Math then?
the first thing that you do is
Register
as a student, which is automatic. Like that'll happen pretty quickly. It's not like a person has to go address that. It should happen pretty quickly. And you get that by just having a pulse. You don't have to prove you're a college student or anything of that nature. It's truly free.
Okay.
I apologize. That's totally my fault.
Oh no, it's okay. I was just confused.
Yeah. Since I'm here.
I have a question.
Go ahead,
For
Aaliyah.
the homework, all the problems that are listed under January 7th/9th,
Yeah.
do we just do all of section 2.3 and 2.4 before we come in on Thursday?
Yeah,
Or is
roughly
there
what
a different
what
split?
I'd like you to do is be working on those this week. In a sense, after you leave today, you should be mostly capable of doing 2.3 and 2.4, these questions here. But mainly what I'd be interested in is getting your homework from you sort of before next week, because next week we're actually starting chapter 4. So you don't want to still be working on it, and I'm going to take points off when next week starts. So as long as you get them to me by, well, Monday, I guess, since class is on Tuesday, if you get it to me by Monday, then you're done and sort of ready for next week. So I don't want anybody
Okay.
still working on those questions when we start talking about, the following Tuesday, January 14th. Before that, it's kind of up to you. However, you understand that chapters kind of progress. And so if you sit here saying, cool, I don't have to do anything till next Monday, 2.6 and 2.8 might depend on 2.3 and 2.4. And so if you haven't practiced those, you might not get as much. It might not be as straightforward to you. So yeah, you'd be smartest to be done with 2.3 and 2.4 by Thursday.
Okay. Also, if we get the textbook, say through Amazon, does it need to be new to have all codes and stuff, or can we get a used one?
No, get a used one. This class does not have an
Okay.
online component. We're doing the problems out of the book because I could have got you into this with Pearson and cost you a whole bunch of money, but no, get the most used, cheapest book you can possibly find.
Okay.
Anybody have any advice on that? Ben and Evald, since you guys have hunted it down.
Chegg.
Mhm.
Okay.
That's where I get my
It's
books.
usually pretty cheap. You can even rent it. I think you can rent
Yeah.
it through Chegg. So
Well,
Yeah, that's what I do.
I just rented mine from Amazon. It was like only $24, which was really good. So we don't have to turn it back in. I won't get to keep it. But
yep, that's okay.
Thank you.
Yep.
Also on the syllabus, it says that we need to do all of our homework in pencil. Is that true for this term or not?
Not
and then
really.
would we just scan it?
Yeah, it doesn't really matter because it's not face to face. So, I mean, I'd still advise you to do it in pencil because you're going to make mistakes and you want to be able to erase it. I would encourage you to become an engineer and get an engineering pencil, and you might have different sizes you like, but I break lead a lot, so the 0.9 millimeter one works better for me. And get a legit eraser, not like a pink one, but one of these high polymer guys, because they do a really good job erasing. And again, I'm saying that for your sake more than mine, but also when you scan things, the scanner sometimes will pick up eraser marks. And so what I get will look terrible and hard to read if you make mistakes. So engineers use this kind of green paper, and it's kind of cool for even one of the reasons this stuff exists is it kind of comes, I don't know if you can see this, but yeah, you got some, Aaliyah. But it comes with a grid on it, so that it helps you keep lined up when you're writing things, because that's one of the things you got to do as an engineer is be organized. And then it also has these little spaces up on top where, in the real world, you could say Johnson project, May 13th, 2022, and you could write some stuff up there as to what all these calculations pertain to. In this class, it'd be cool to have, this is question 2.3, 2.4, and the way they're worded too is kind of weird. Is like that first one is question 2, it's 2.3.2. So it's kind of an unusual book in that way, because they just proceed through the entire chapter. When they get to the next section, they just keep moving. It's not like questions 1, 2, 3. You're clear up to question 97 and 2.8 because they just keep the numbering system going. So that's kind of interesting.
Another thing that I just thought of is, do you want one question per piece of paper?
That's a good question.
do you just
I don't
keep-
care. If you do choose to kind of save some paper, at least have a little bit of space between each one of them,
Right.
so that it's really clear. Because when I'm grading, I'm expecting, because you know the right answers, and I'm going to look your work over, but I'm expecting if you don't get the right answer that you and I are having a conversation until you do, because you're going to do a bad job on the test if you do anything else. But I at least want to be able to, look things over. I want to be able to read your work. And so as long as there's a clear space and you've clearly told me, here's the next question, and, something that tells me you went to a new problem. What I don't want to see is like one question's over here and another question's over there and another question's over here. And like, yeah, I got it all into one page. There's obviously a argument for that, but, a balance between those two. Yes, we don't have a lot of questions in this class. You won't even burn up one tablet because of the limited number of questions I'm assigning. I would say for your thinking's sake, and to not feel like you're all, you got to make your figures really tiny and all that stuff to fit them in there. Like, yeah, spread out. It's smart to do every single question on a different on a different page, in my opinion, but I'm not going to hold you to that.
Thank you. And I'll see you guys Thursday.
Sounds good. See you, Leah.
Awesome. Yeah, and I'm looking at my syllabus right now, and I have posted that my office hours are from 12:30 to 1:30 every day, Monday through Thursday. So my intention is to be at this sort of permanent Zoom link right here, to be just sitting in there, and I'll be doing my own work if nobody shows up, and that's also for my calculus students. But this is a small class, and you need to take advantage of that. If you're doing this with 30 students, you don't have near as much access, but like, this is neat stuff just to know as a human being, just to live in the world, even if you weren't an engineer, if you have the math skills to know this. And I'm not teaching this to hear myself teach. Like, if you don't get it, then I'm failing. Like, I want you to understand it. And I'm more than willing to spend extra time with you to do that. So hit me up at those hours for sure, just because you'll be able to find me there, but also outside of that, we can do too. I gotta make a note to show up to that. I kind of forgot about that.
Did you say so is all the homework due on Sunday, the next?
As long as you give it to me really before the next class, like even Monday would be fine. And that's why I didn't put a due date on here. There is one, but I didn't put it on here. So even Monday would be fine.
Before the next class?
Yeah,
Okay.
just before the next class starts.
So our stuff for this week would be due, or the 2.3 and 2.4, is that stuff due Thursday? Or is it just kind of?
No, I'm not going to collect it. I really would prefer you. I actually don't care how you send it to me. You could send me 2.3 and 2.4, scan those and send them to me separately, and then later scan 2.6 and 2.8, or you could wait and give it all to me at the same time. I actually don't really care. For my purposes, it's up to you. As long as I get it all in some form before next week, I don't care.
Okay.
So, I mean, send it to where?
Just to my email is fine. If you just attach it to an email.
Okay.
And I need to send you guys an email about that.
All right. Bye, Doug. Thanks for the class.
Yeah, see you,
Bye,
Dan.
everyone.
Glad you're in.
So, and you was talking in the syllabus about projects. Is that going to be like for each person, or is that going to be like a group project?
Generally speaking, I want it to be groups because, again, like in my calculus class, I'm interested in you getting it right. But I haven't taught this as long, so there won't be a ton of them, and I don't even. And whether they're in class, like I have time in class for you to work on them, or whether I give them to you like after a test and you work on them, kind of to be determined. Some of them are physical though, and that's what's gonna be hard. This tower crane project is super cool, but it involves building a truss bridge, a truss design and testing it out of balsa wood, and so we can't even get together to do that. So that'll be pretty minimal, I guess, is what I'm saying.
Mm-hmm.
Sometimes, with a small class, like it might be the entire class is working on it together.
So far, this is all of the students in the class.
Yeah, it's really small.
So
I mean,
it's maybe 6 of
engineering.
us?
Yeah, engineering's pretty small still here. It's a pretty small school to have
Mhm.
to have 10 people that are going into engineering. As going through in a sequence is be pretty large for a small school like ours. So.
Okay, so basically, the biggest problem is going to be just finding the angles, right?
Say again, finding what?
Like angles for the problems, because I mean, the last problem, it just was like building the angles for the most of the part.
Yep.
Okay.
Being just really good at kind of basic geometry and working your way around angles and sides is going to be a huge part of this class.
Mhm. All right. Okay. Thanks, Doug.
Yeah. See you later, my friend.
See ya.
Bye-bye.